So, good afternoon everybody. My name is Grillo, and today I'm going to talk to you about growth and remodeling statistically oriented fiber-reinforced composite materials. And before I start, I would like to thank the organizers for letting me be here today, and all of you for your patience. I have to say that I am pretty new to the field of higher gradient materials. So, in the very first part of the presentation, I will also try to show you some work in progress. You won't find anything we've been discussing in these days, because I got acquainted to these beautiful theories since I've known Francesco, so please forgive me. Okay, so I should say this is a joint work with my colleagues, Gabriel Wittum in Germany, Alexander Tomic and Salvatore Federico of the University of Calgary in Canada. Okay. So, what are we talking about? The kind of biological tissue we would like to model is articular cartilage. Articular cartilage is a thin layer of tissue that covers our junctions. Like, for example, the junction of the knee. So here you see a sample of articular cartilage which consists mainly of a matrix of proteoglycan and those fibers you see there are collagen fibers, and there are also cells called chondrocytes.
You are already on M&MoCS.
Yes.
In the first slide.
In the first slide. The surface that you see at the bottom is the bone interface, and the surface above is called articular surface because there is another layer of articular cartilage just above it, which is not modeled anyway. You see that the distribution of collagen fibers is statistical, so one is able to find a probability distribution of finding a fiber aligned along a certain direction at a given point of the tissue, and experimental measurements provide these mean angle that you see over there and the variance for a Gaussian type probability distribution density. We would like to model this composite material at this stage in a very simple way. So first of all, we will get rid of the fluid, and we will propose a reduced model in which only a solid phase composed of a matrix and fibers is present. Of course, you have to consider that matrix and fibers exist with some volumetric fraction, and the sum of those two volumetric fractions has to be 1 at all times and at all points. Further, we assume that this is a mixture with constraints. The first one is that matrix and fibers move with the same velocity, and the second assumption is about incompressibility. So we assume that both the fibers and the matrix are incompressible materials. Of course, these have implications. First of all, if you assume incompressibility, or let's say you say that those ratios are negligibly small, then you're saying that J is equal to 1, that the divergence of velocity thus is 0, and that capital phi f, which is the Piolan transformation of the volumetric fraction of the fibers, has 0 time derivative. But in general, it can be a function of coordinates. As I said, those are statistically oriented composites. To model the fact that these articular cartilage can be treated as a transversely isotropic medium, we firstly introduce the set of all directions in space, H2, and a probability distribution which is firstly defined as a function of M and Q. M is the vector over there. I don't know what I have to laser here. M is here, and since we are requiring transversely isotropy, basically the probability density distribution is allowed to depend only on this angle. Of course, we assume that P depends on the mean angle, but we are assuming that it doesn't depend on the variance. in the sense that the variance is given. This is an approximation, of course, because it is a function of position, but let's assume that it is a constant for the time being. In particular, we are giving to G, then we have to normalize it, this Gaussian-like expression. Okay, we put ourselves in a purely mechanical framework, and what we would like to study is that the formation of this composite, as I said, under the assumption of incompressibility, which means that we have to compute the components of the formation plus the Lagrangian multiplier expressing pressure, and the reorientation of the fibers, which we call remodeling in this context, by introducing a structural degree of freedom whose dynamics has to be described by appropriate balance laws. And in this sense, we differentiate our approach from some other approaches found in the literature in which the so-called remodeling law was determined by either, specifying the angles giving the alignment of the fibers as internal variables. For us, the remodeling variables, which is in this case the mean angle Q of the probability density distribution, is not an internal variable but an additional degree of freedom, so we have an extended kinematics, and we will need an appropriate balance law. And these ideas, well, in the case of remodeling, was published by Olson and Cladrinh in 2008, but the idea about growth mechanics is, it was published by Di Carlo and Quiligotti in 2002. There is another paper about plasticity by Cermelli and co-authors of 2001, and a paper of Gartin of 1994 about Kahn-Hilliard model and Alarcon model. Okay, so those are our unknowns, the components of deformation, pressure, and Q, and the way we treat the dynamics of our system is first of all by introducing the virtual powers. So this is the external virtual power, which is a function of virtual velocities u and virtual velocity omega. This is the virtual velocity associated with the mean angle, and here you recognize the standard terms, and here an additional term which is non-standard, which is due to remodeling. The internal virtual power consists also of a standard term and a non-standard term. So also in this case we are starting with zeroth order theory with respect to the augmented kinematics. In strong form, we have the standard form balance and the balance of remodeling forces, which amounts to say that the internal interaction Z int must be balanced by the external interaction Z ext. So, just to give an idea of what Olson and Cladrinh modeled, they had in mind to model remodeling in the case of arteries. So when you study arteries, you have, this is of course an oversimplified picture, such a pattern of fiber reinforcement. This is assumed this is a tangent plane taking on the mantle of the artery, which is given a cylindrical shape, and you have this pattern of fiber rearrangement, which preserves axial symmetry.
Excuse me.
Yes.
Can I ask you how they are connected, these fibers?
As far as I know, in reality, you have 3 layers in the arteries, and as far as I know, they are not connected. They are just filling the layer by making, being coiled according to this pattern. If you take, of course, just one surface, apparently they are overlapping themselves, so as far as I know.
They are embedded in a matrix?
Yes, they are embedded in a matrix. The difference is that we are going to model such a situation, again. You see here, this is the knee. This is the symmetry axis, and those are the fibers. So, telling something about the remodeling variable. We introduce the probability density distribution, and we give it an evolving parameter. there is an S there because also the variance could vary in time in general, but as I said, we are assuming that it is fixed just for this academic example. And so the only parameter which is allowed to vary is Q. And what we are searching is an evolution law, sort of reorientation of the fibers described by this angle. To do that, we have to introduce some constitutive framework. This is done by providing the stored energy function of our composite material, which is written in this form. So 1 minus phi f is actually phi m, the volumetric fraction of the matrix. This is the energy of the matrix, and this is the energy of the fibers, which depends on the distortional part of the Cauchy-Green deformation tensor and on Q. For simplicity, we assume that the matrix is isotropic and hyperelastic and independent of Q, and we take a simple Neo-Hookean energy, whereas the fibers are assumed to give both an isotropic and an anisotropic contribution, which is given by the sum of those two terms. Again, we take a Neo-Hookean law for the first isotropic term, and for the non-isotropic term, in fact, transversely isotropic, we average this energy, small w, with the probability density distribution. Inside this energy, there is an Heaviside function of the fourth invariant, which sets the energy equal to 0 when fibers are not stretched. So this is non-zero only when fibers are stretched. Okay, then the stress, in fact the deviatoric part of it, is given by the superposition of three terms. Each of them has to be multiplied by this operator, with the transpose of which is defined over here. And again, this is the isotropic contribution, this is the anisotropic contribution, which is given by the average over all directions of this derivative weighted by the probability density distribution. And here is the total stress. Now, in order to get an evolution law for the remodeling variable, we have to find, first of all, some admissible constitutive law for the internal remodeling forces, Z intern. And we ask permission to the dissipation inequality. Here I'm taking the time derivative of the Helmholtz free energy density inside a volume M, subset of the reference configuration, which is fixed, and this is the net power. As you see, this is the standard term, where SD is the deviatoric part of the second purely critical stress tensor, and this is the power given by the internal force of remodeling. If I localize, I get this information, which means that I'm looking for expressing Z in as a constitutive function of all these variables. You see that the first three are non-dissipative variables in general, and this omega is the velocity. So if I call by y tilde the dissipative part of this force Z int, dissipation has this form. It will be 0 if omega is equal to 0, and it will have this form otherwise. I would like to spend a few words on that, because usually, since this model by Di Carlo and Piligrotti was published, many people reached conclusions about the attainment of equilibrium very, very, very fastly, because it's nice to have an additional non-standard force, because it helps to nullify let's say, it helps the enrichment of a stationary state. But many things should be said before. It is, of course, an approximation. First of all, one should say something about dissipation. For example, we are assuming that dissipation is a homogeneous function of degree n. In few seconds, it will be of degree 2, actually. And therefore, it will have this form, which leads to a sort of Onsager relation relating the dissipative part of the remodeling force with omega. But in principle, I may choose also a rate-independent form of the model, so dissipation which is homogeneous of degree 1, and just to mimic plasticity. Why not? I might also have something like this. But since we want to make things very, very simple, let us assume that n is equal to 2, and let us write, just for completeness, how the rate-dependent model of remodeling reads. So again, we have the balance of remodeling forces with this internal force expressed constitutively, where y tilde is given by this product. Lambda is just the list of all variables which are not related to dissipation. And so this is the evolution law we were looking for. So you see that it is nice to have this force which is external now, because I can tune it in such a way that it is that the right-hand side of this equation is 0, and so I lead the system to a stop. I will set omega equal to 0 by tuning z external. And my claim is this that is not always physical. I mean, there could be many other situations. So this is a brief summary of the model, and I would like to speak of the case in which the bulk external forces are set equal to 0. So actually you have a problem of this type. And just to make a very easy example, assume that a cylindric geometry, like in the case of an artery, and assume that this tube is being inflated. So you give this deformation, which preserves axial symmetry. This is the deformation gradient. This is what the incompressibility constraint implies. And you can start the calculations. So I will show you some results. This is the first Piola-Kirchhoff stress in radial here and tangential directions for the initial loaded configuration and the remodeled configuration. So you see that remodeling is such that the distribution of stress, especially the tangential stress, tends to become more uniform. This is how the remodeling variable, so the mean angle of the probability density distribution, evolves in time at different values of the radius. So here we are on the outer surface where no force is applied, and you see that the remodeling is very, very small. Practically, the angle remains equal to the initial condition. But when I go to the internal surface, where the force is applied, well, then I have the layers that remodel the most. What is interesting for me is that the derivative of the energy with respect to the remodeling variable attains a stationary state without the need of tuning any external force. The reason is, so what has been done by other authors is to say this external force is equal to this derivative computed at some value of the target angle, which is fine to me. But in our case, the choice of the energy was independent in a sense was independent of the remodeling variable. The remodeling variable appears because I have to average according to the probability distribution. And this leads to this formula where you see that you have the average of the product of the angle alpha, generic, times the potential energy W, Fa, minus the product of the means. So this is basically a fluctuation. So what I'm saying is that when fluctuations cease, remodeling asymptotically ceases as well. So, just a remark. Switching off the external remodeling force means that, granted the balance of internal remodeling forces, our system this S shouldn't be there, naturally tends towards a stationary value of Q, which depends only on deformation and the volumetric fraction of the fibers. Of course, this model has a main drawback, and the main drawback is that the functional form of the probability density distribution on which the whole theory grounds is assumed to be known from the outset. And so, given the probability density distribution at some instant of time, for example, the initial T0, the structural reorganization of the material is constrained to preserve this functional form for always, basically. We are working on how to relax this hypothesis by treating the probability density distribution as the remodeling variable. We are working on that, and for this we need, of course, a theory in which the energy depends also on the gradient of the probability density distribution. Now I would like to speak of some work in progress. Yes, perfect, some work in progress, which is to put growth into this model. So, the main ingredients of the theory will be, of course, the Bilby-Kruner-Lee decomposition of the total deformation into an elastic and a growth part, which growth part will be treated as an additional kinematic descriptor, so not as an internal variable, and one invokes the principle of material uniformity, which should be modified in order to account for the fact that, strictly speaking, the material is no longer uniform because you have the fibers, which in principle have different properties from the matrix. And in this case, you have to find thermodynamical admissible laws for determining the new variables of the reached kinematics. This is just an attempt by myself to learn what we've been discussing in these days, but I will get rid of those terms immediately because I still have to understand precisely how to treat them. And let's go back to a theory of zeroth order along with the force balances, now written in strong form, so I underline that this is first order theory and those two are the zeroth order theory. You have to write dissipation. In this case, the driving force of growth deformations is the combination of the Mandel stress tensor and the internal force T intern, which should be now studied according to Constitution, and this is as before, the dissipative force related to remodeling. As I did before, however, let me switch off the external forces, and then, by means of the balance, this implies that also T internal and Z internal are zero. So this is the dissipation, exactly as before. And if I get this nice form of this term, by choosing these duality pairs, as kappa is K is the second Piola-Kirchhoff stress tensor written with respect to the natural state of the material, then I might think of writing, in the case of a transversely isotropic material, this form of evolution law for LG. But you see, this is what happens on a fiber. I have to average. And when I average, here, you see, since I4, this I4, this here, depends on, of course, A, kappa, and A kappa is also here, I cannot factorize. So I have to keep these things, these terms. Recall that the stress is made of an isotropic contribution and this anisotropic contribution, which is given by an integral. And so what we will find is that remodeling is coupled to growth in this way, according to our model. So it will contribute directly both on the stress and on averaging this tensor. And this is a list of literature, and I would like to thank you very much. I don't know what happened. Sorry. There were some pictures, but I don't know what I did. Sorry, I cannot. I will show the pictures later. There are the pictures.
Question number one.
Yes.
I correctly understood, you obtain your effective energy density by summing the densities of the phases weighted by the volume fraction.
Yes.
So my impression is that this should be regulated for the mechanical response from either direction to the fiber parallel.
Yeah.
Do you think it makes sense to do some complicated interaction?
It might make sense. It might make sense. This is a model used. Oh, sorry. This is a model used for cartilage in general. Okay. It might be you're right, and we should think of more involved terms. But for example.
That's like all the phases are just in parallel.
Yes. Well, let's say that also one should account also for more invariance, to be more precise. Yes, of course. But this is just to make things with MATLAB in one thing.
We have time for one question. Yep. Part of the what we call is affected by the chemical environment of the fluid.
Of course, this is just not considered here. It was done theoretically. I mean, we wrote down all the set of the equations, but we haven't done computations yet. These will come. So at the moment, we just got rid of all of everything that was too difficult at the moment. But you are right.
One more question.
Remodeling cartilage happens if the loading conditions are changed by accident or by something else. Therefore, from your benchmark test, you should have a result of a probability distribution that you can find in real cartilage for your...
Yes, so the probability density distribution was measured in real cartilage. The benchmark could be also unphysical at this time of the, by unphysical I mean not suitable for cartilage. This is perfectly right. But the only model using these, let's say, augmented kinematics was done for arteries. So just to test, just a proof of concept, then we use the same benchmark. But of course.
I think this is it.
Thank you very much.